Alex, are you there?
I am indeed. Hello, Manjit.
Okay,
Can you
so
hear
good
me well?
morning. Welcome. Yes, we can hear you perfectly.
Super.
So you see, another colleague, and when I talked about building collaboration networks, this is what you do, because throughout your life, you identify with people, you collaborate, you continue your collaborations and networks. So when you need them, they turn up when you want them. So Alex is perfectly one of these people. So he has a master's degree in mathematics from University of Cambridge, a doctorate from University of Oxford. He's worked at CERN and PSI, Paul Sharing Institute, when he worked on the proton therapy facility, ProScan. He was a CERN physicist, beam physicist for a long time, and just recently we've lost him, but on the other hand, he's moved to be an associate professor at the University of Medical Center of Groningen in the Netherlands, where he leads the accelerator in radiation physics research at Particle Therapy Research Center. So first, welcome, Alex. Second, we asked Alex a really difficult task. And as usual, he rose to his challenge, because we talk about simulation beams, all of these things. But you know, simulations are used in all aspects of hadron therapy. So the student volunteers gave him a task list. So Alex, please go ahead, and thank you for rising to our challenge.
Thank you very much for this kind introduction, Manjit, and hello, everyone from my side. Let me start sharing my screen. And I hope in a moment you will be able to see my slides in full screen.
We can.
Can you see them? Okay,
yes.
Super. Excellent. Well, yes, thank you very much for the introduction. And indeed, you might know me from my past work at PSI and at CERN. Since recently, I joined the University Medical Center Groningen, where I will be working on Particle Therapy Research Center, PARTREC. And yes, I was asked to talk today about the use of simulation tools for accelerated physics and specifically for hadron therapy. So I will try to give an overview lecture, and all questions are welcome. I think because of the digital format of this lecture, it would be convenient if the questions are asked at the end. But let me give you just a couple of words of motivation why the simulation tools are useful. Well, when you design machines for hadron therapy, you have a wide range of different processes which are involved. So first of all, you have, of course, the beam, the generation of the beam, the acceleration of the beam. This summarizes very general what the beam can be, but in the case of hadron therapy, it's typically a proton or ion beam. And you have a statistical distribution of particles there by their properties, for example, their position, their angle, the momentum of different particles. So this is on the beam side. Then, of course, you have the propagation of the beam in matter, or in case of colliders. So this is, of course, not a medical application, but there you have the interaction between the colliding beams. But for the purpose of hadron therapy, you have propagation in different types of matter, so different atomic composition, different densities, arbitrary geometries. And there you have a variety of different interactions, right? So you have the strong interaction, weak interaction, electromagnetic interaction, and to bring it down more specifically, you have production of bremsstrahlung, neutrons, etc. So it's a very large spectrum of different processes. There is also activation of the material. You can have magnetic and electric field inside of the patient, for example, if you are treating while the patient is within an MRI machine. And then, of course, you have the detection of the particle. So you want to be able to precisely control the dose you are delivering. And in order to precisely control it, you actually want to know what is the dose supposed to be at this location. How does your detection influence the beam parameters, right? So there is also interaction of the beam with the detection material. And so all these processes can be simulated. And in order to have a good control of the beam, you have to have first a functional simulation before you actually start building a machine and start applying the beam. So all these processes, which I have mentioned, they are governed by statistics. Many of the distributions of the beam are statistical. The interaction with the matter underlies, the statistical laws underlie the interaction with the matter. And also for the detection, usually you do not want to have a position and angle and energy of each individual particle, but you want rather to have a distribution and maybe also some parameterization of the distribution. And so because of that, this lecture will actually start with a very brief introduction to statistics. Then I will give also a brief intro into particle transport and how do we describe particle beams. And then I switch to Monte Carlo simulations, which basically combine the both. And finally, I will speak about the software codes which are available for the Monte Carlo simulations. Now, this presentation doesn't attempt even to go in depth in every of these topics. So the goal is actually to give you an overview and conceptual understanding of each of the topics. And then if you are interested to know more for statistics and for Monte Carlo, you can, well, basically do it in every university. For the particle transport, there are excellent courses by CERN Accelerator School and also by John Adams Institute, a graduate program. And also for many of the software code like MEDEX, like Fluka, like Jan4, there are excellent schools. So for Fluka and Jan4, for example, there are excellent CERN schools. You can join them if you intend to use these codes and if you want to know more about them. So the lecture is rather to give you an overview and to see how these things match together, but not necessarily to go in depth about each of them, because of course, one would need much more time. All right, so let's start with the statistics. The basic definitions in the statistics you have probably already seen either in your high school or in your university courses. So a random variable describes an outcome of a process which cannot be predicted with certainty and only is governed by probabilistic laws. This can be something fundamentally physical like quantum mechanics, but it can be just because we do not know the exact parameters of for example, a particle propagating. And the probability of the particle having a specific value, for example, of its position, momentum, of angle, or whatever else, the cross-section, is described by probability density functions. They have a number of interesting properties. So, for example, they are either zero or positive. You cannot have a negative probability. They are unit normalized. So the overall probability for a probability density function is 1. So something always happens. And if you want to change this, like for example, if you have an interaction of the beam with the matter, within a period, it can happen or not happen, depending on the cross-section. So then you have to multiply this probability density function with the respective cross-sections. And most importantly, the integral of the probability density function between values a and b corresponds to probability of the random variable x being between a and b. Okay. There are a couple of central definitions in the definition of the from the probability distribution function, such as expectation value. Expectation value is the same integral as here, but just multiplied by x. And so this typically gives you then what on average x will be. And then you can also see how the distribution of x's deviate from what x on average is supposed to be. And this is given by variance or the square root of variance, which is called standard deviation. Now, there are very many probability density functions. So I give you just a couple of important examples, but basically everything which satisfies the criteria defined at the previous slide can be a probability density function. So the couple of examples which I want to bring up is the most simple one is a uniform distribution. There you have equal probability of x being between 0 and 1 and 0 everywhere else. So this is rather, let's say, theoretical distribution. You don't see it too often in actual nature, but often this is the goal of the optimization which you are trying to achieve. So, for example, if you have a tumor or a patient with a tumor, and the tumor is located in one specific region, then the dose which you want to apply is 100% at the location of the tumor, and 0% everywhere else, so that you do not deliver dose to the healthy tissue. And so this can be often seen as a goal of your optimization, but this is, of course, not necessarily a goal you can achieve 100%. Interestingly, this is also how a strongly collimated beam looks like idealistically. So if you, for example, spread the beam very wide, and then collimate a very big share of it away, then usually you have a plateau in the non-collimated part. So this is one of the ways of getting distribution which approximates the uniform distribution, but of course on the cost of beam intensity. So of collimating away a very big share of the beam. Another distribution which you certainly have encountered and dealt with in the school is the Gaussian distribution. So there you have a Gaussian peak and then a distribution function around it. So you measure it in sigmas, and the standard deviation is equal there to the root mean square. And the good thing about Gaussian is that if you go far enough, so many enough sigmas, 3, 4, 5, 7, then the chances of the particles being at this distance decrease enormously. And so this is a convenient distribution if you want a very controlled beam and also low losses at very far ends of the distribution. If you look, for example, at the nature of distributions, which or nature of parameters which have Gaussian distribution, you see that, for example, the height or the weight of people in this virtual room, if you would plot them, you most certainly would get a Gaussian distribution. Also, if you propagate a beam through some materials, so be it air or, for example, vacuum windows, beam monitors, the beam is interacting with this material and being scattered to some degree. And if the scattering is sufficient enough, then you get a Gaussian distribution as well. If you have, for example, the beam in the patient body, and even if you start with a so-called pencil beam, so zero angle, zero spread, after the beam is scattering in the patient body or in water, you get a Gaussian distribution. Another very common distribution is exponential. So this you can see in many forms. Some of them, for example, Pareto distribution, are applicable to very many examples from nature, such as, for example, if you plot the size of the stars against the frequency, how often you can find them, then you will see that you can see a very little number of huge stars and very large number of small stars. The same with the meteorite. So, there is this big fear of a big meteorite hitting Earth, but this can be statistically at least predicted what the chances are of a meteorite of a specific size to indeed hit the Earth. And we're being bombarded every day by many meteorites, which are very small. So the probability of them existing is very high. But then, of course, a huge meteorite like the one which hit the Earth about 65 or so million years ago, this happens extremely seldomly. Also, an important property is distance between DNA mutations. This applies to random DNA mutations, but this applies also if you do proton therapy or particle therapy, and you induce damage on DNA. So distance between the locations of this damage is distributed exponentially. You have more entries at a low distance, and then you seldomly find segments which have been completely untouched by the radiation. Also, some man-made or human-made parameters can be distributed exponentially. So this I find quite interesting. For example, if you look at the size of the cities worldwide or in every specific country, this follows the exponential distribution. Number of citations per publication, since we're in academia, you can see, for example, if you look at the authors and the number of citations which each author has, you have an exponential curve. But also, if you look at every specific author, you have an exponential curve. There. So there will be a couple of papers which have extremely high number of citations, and then a majority of the papers which even this maybe highly cited person has written have a very low number of citations. Another is wealth across people. So if you look at the overall wealth, you'll see that the number of individuals with extremely high wealth is rather low. but the number of individuals, the closer you get to 0, basically, the higher is the number of individuals. There are a couple of important parameters in the distributions of the probability. So I mentioned before, for example, the mean. The mean is the integral of p times x over the whole period. So if you have a discrete distribution, it's basically the sum of all the entries divided by the number of entries, right? And I list them here because I want to be precise about it, and also for you to be able to distinguish between different terms and to know the terminology. Mean is the same as expectation value, but it's not exactly the same as average. Average is what you get out of a sample. So mean is a property of probability density function, right? If your sample is big enough, so n is going to infinity, then the average of the sample is converging to the mean of probability distribution function. And this is, by the way, is called central limit theorem. So this is quite an important property of probability. Once the number of n hits infinity, basically your realistic distribution you get out of the experiment is the same as probability density function. Now, of course, in reality, n cannot get to infinity. Then there is another value, which is called mode, and mode is basically a maximum. Where does the curve has a maximum? So a derivative of this probability distribution function has a 0 there. And then you have a median. Median means everything which is below this value has the 50% of entries that they are below this value, and 50% of entries are above this value. Okay, and as you can see, the mean, the mode, and the median can be very different. So here you have, for example, the log normal distribution. If you take the logarithm of this distribution, you will get Gaussian. You see there is a parameter which determines how asymmetric the distribution is. If this parameter is low, then your mean, mode, and median are close by. But if this distribution gets very asymmetric, then you see you have the maximum here. The median is already, well, factor 3 above the maximum, and the mean is almost factor 10 above the maximum. So it shows you that these values are not always the same. And people often intuitively mix them up because you often in the school deal with Gaussian distribution, and Gaussian distribution is symmetric and unimodal. Unimodal means it has only one maximum. And because of that, there the mean, the median, and the mode coincide. But it's of course not the case for all the distributions. So you maybe know this joke that there is a bar and 200 people are sitting there drinking beer. Suddenly Elon Musk walks in, and then on average everybody is there a billionaire, right? So this is of course on average true, but it doesn't. It's just because the average moves with one individual entry. Now the variables can be random, but they can still depend on each other. So you can have a number of variables which have some type of dependency. So here, for example, in the diagram on the top right, you see the price of a house as a function of its square footage. And you see the measurement values, so to say, are the red circles. And you see there is clearly some dependency. So the higher the footage, the higher price. Okay. So you can fit a linear polynomial through it. So this is the green curve, p equals 1. And the linear polynomial is called correlation. Now, correlation, and this is one of the central things which one should learn during a statistics course. Correlation doesn't mean causality. It can mean causality, but it doesn't have to. So just again, as a joke, here on the bottom left, you see a number of people who drowned by falling in the pool and films with Nicolas Cage. And you see that over the years, there is a very high correlation between these two values, but it's highly improbable that there is actually a causal relationship. So it can be that the variables are completely independent. It can be that one is causing the other, or the other is causing the one. Or it can be that there is a one underlying cause which causes the both variables to be correlated, but it doesn't mean that immediately A causes B or vice versa. Okay. Now, when you have a data set, you can different functions through it in order to approximate it. And for example, if you look at the polynomials and you look at this distribution, you can fit the first order polynomial in green, the second order polynomial in blue, and for example, a 10th order polynomial in gray. And the higher the exponent of the polynomial, the better you match the points, right? So this is obvious. But does it mean that the model prediction value improves? So you see clearly here the green curve probably helps you to predict what would be, for example, outside of the scope of which is shown on the graph, or in between. The blue curve probably helps as well, but the gray curve is probably already off, right? So this is your intuition, and this intuition is correct. What you can do if you want to pick what is the suitable model to actually see the dependency of the variable, then you can subdivide your set, if it's large enough, especially. You can have, for example, a so-called training set. So this is what you base your approximation on. And then you have a test set, which can be, for example, 10 or 20% of the overall number of entries, where you see how does the test deviate from the prediction power of the training set. And so for this specific example, you can run the numbers and you can see what is the exponent of the polynomial which you want to fit. And then you can see, okay, with the first, so with the green curve, you get already a decent prediction power for the quadratic, and so up to the exponent 4, you get very decent prediction power, and indeed it fits even better than the linear correlation. But once you start getting to the higher polynomial, the test values error start to increase, and that means that you are already in the not anymore productive domain, right? So you are overfitting the curve, and the prediction power of the system decreases. It doesn't. I guess the message from it is the more precise model, which describes the past data, is not always the most precise one to predict what the future data will do. So this is called bias variance trade-off. Okay, so far to the statistics. Now let's switch to particle transport. Now, just a couple of basics. So if you look at one particle in one dimension, then you can describe this particle by a very simple two-vector with here, for example, U1 and U1 prime, which tells you the position and the angle of the particle at a specific location. Okay. And then you can propagate the particles through a part of the beamline, and you can have different magnets there, you can have scattering, etc. But then you can see, okay, what does the particle do at location 1? So here you have location 0, and then at location 2. And the approach, which is taken in accelerated physics, is that you can calculate the position of the particle after the propagation from the initial position. So you can have a transport matrix for every single interval of the beamline. So for the transport through this part from 0 to 1, you have M1, and from 1 to 2, you have M2. And the most interesting and most convenient thing is that with this approach, you can actually calculate what is the transport matrix from the location 0 to 2 directly, because with the linear algebra, you can just multiply the two matrices and then apply it to the vector U0 and U1, U0 and U0 prime, and then you get U2 and U2 prime. So you get immediately a result. This is very convenient because then you can design every part of the beamline separately, and if you want to plug them together, you just multiply the matrices. We live, of course, in spatial dimensions, and so because of that, the particles are typically described by 6-dimensional vector. Now, in reality, you don't have, of course, only one particle, but you have a whole particle beam. So what do? Well, you can plot the position and the angle of each individual particle on the so-called phase space diagram. So you have U and U prime, and then each particle is just a dot on the diagram. But if you plot all the particles of the beam, what you typically get in, let's say, the first order is an ellipse. And this is so-called phase space ellipse. So this describes where the beam is. And then you can describe, for example, the size of the beam over the whole beam line by so-called emittance. So emittance is basically the surface of the area occupied by phase space ellipse. You can have, for example, 2 sigma. If the distribution is Gaussian, you can say, okay, well, I do a cutoff at 2 sigma in all planes, and then what is my emittance? If the emittance is big, you have a beam which is large and is going in all possible directions. If the emittance is small, then you have a very, very small pencil beam, which is parallel. Okay. What does the beamline do to such a phase space ellipse? Well, for example, you can start with a positively correlated phase space ellipse. And what does it mean? It means that the beam is diverging. So the particles which are, for example, already on the right, they have also the angle, which is more frequently on the right, to right, right? So then the beam is going apart. But then you can have, for example, floating elements like the quadrupole, which focus the beam back. And so what they do is they invert this correlation, and you get a negative correlation between u prime and u. The beam is then converging. The particle which is on the right has an angle which is pointing to the left. Okay, so this means there is negative correlation between the angle and the position. And then, of course, if the beam is converging, at some point you will have a focal point, right? So this is where the beam waist is. And then you see again, you have a vertical ellipse, which means the beam is very small in u dimension. So this is why it's focused. But if it's small in u dimension, it's large in u prime dimension, right? So the focal point is where the angles of the particles are the highest. And then, of course, after the focal point, the beam starts diverging again. Okay, so that's the description of the beam with help of the phase space diagrams. Now, how do you solve the equations which govern the transport of the particles? Well, you have different approaches. So you can have the analytical approach, and especially if you have a very simple system where only Maxwell's equations count, then you can use it. You can have so-called spectral approach, where you use out the symmetries between the different particle locations and also the fields. But this is only applicable for only very restricted number of cases. Then you have numerical integration, so where you basically use the numerical methods for the systems where analytical approach doesn't give you any result. And you have Monte Carlo methods. And these are the ones which I will talk about in the coming 10 minutes or so, because they are in the recent years the most popular ones. Basically, they require big calculation power, but less interaction from the side of the user. And because the let's say the person hours are becoming more expensive, but the calculational power becomes less expensive, the shift over the last 20-30 years has been more and more towards the Monte Carlo methods. Now, what are Monte Carlo simulations? Well, it all started in Los Alamos. As you know, this was the laboratory which was responsible for the development of the nuclear weapons. And in 1946, when the Monte Carlo method has been introduced, the laboratory was already successful in developing and also using the first nuclear weapons. And during this time, Stanislav Ulam, Richard Feynman, and John von Neumann, so very big pillars of particle physics, they have come up with the approach to simulate the processes which take place during the ignition of the atomic bomb with help of computers which were just introduced during this time period. And the principle is the following. You define a domain of possible inputs. So this can be positions of the particles, but also, for example, the cross sections. Then you generate an input which is randomly distributed or pseudo-randomly, and I will explain in a couple of slides what it means. Then on this random input, you perform deterministic computation, right? So the computation itself is not random, and then you basically get out the results. So just to give you a simple example, here you have a square 1 by 1, and you can just define what is within a radius of 1 from the 0 point, and everything which is within the radius you put as a red dot, and outside is a blue dot, and then you can just randomly assign uniformly particles within this square, and you can calculate how many red particles do you have over how many particles you have in total, and from that you can calculate pi. And so you see you have increasing number of particles, and the pi is getting more and more precise when you increase this number. Now, I mentioned pseudo-random number generators. You have a random system, but you have to somehow simulate it with a computer. And apart from quantum computers, which are not very common to use, the normal computers are completely deterministic system. So you cannot have a true randomness in a normal PC. What does it mean for Monte Carlo simulation? Well, it means that you have to mimic the randomness with deterministic algorithms. How it is done is with help of so-called pseudo-random number generators. So what you typically do is you plant a seed. The seed is just a number. And then from this seed, you calculate a sequence of different numbers. Okay, so you start with x1, and then you go to any number xn plus 1, whatever the distribution n requires you to go to. It's important that different seeds will yield different sequences. So by changing the seed, you can modify the whole sequence. Okay. If you look, for example, there are special algorithms which are capable of generating these pseudo-random numbers. They have been described by mathematicians, and for example, the one used in FUCA is so-called RM64. There are a couple of requirements on these pseudo-random number generators. First of all, what you want to generate is a uniform homogeneous distribution between 0 and 1. So this is the uniform distribution I've shown several slides ago, the idealized one. You want to have a long period so that if you start with a specific seed, the numbers do not repeat and you do not end up very quickly, at least, at exactly the same number. You want to have a repeatability, which means that once you start with a specific seed, using the same algorithms, you get exactly the same random numbers, pseudo-random numbers. You want to be able to jump ahead. So this means that calculate xn plus 1, you do not need actually all these numbers. You can calculate it directly from x1. And this helps you to parallelize processes, because if you want to simulate 1 million particles and you have 1,000 cores, then you don't have to calculate it with one core. You can do it with 1,000 cores simultaneously. So on each core, you basically can simulate 1,000 particles. And this you can do more efficiently if you can calculate the sequence number n plus 1 immediately from x1 and do not have to calculate them one by one separately. And then you want to have portability, which means that these numbers are not dependent on the machine which you are using, or the software, programming software which we are using, or even the operation system. And efficiency, so that you can calculate it within a reasonable amount of time. Now, the realistic distributions are, as mentioned before, not necessarily the uniform ones. And so what you do is usually you define a function by which you have to multiply the uniform distribution to get the probability density function which you actually require. So this is the way how you get from the uniform distribution to a Gaussian, to an exponential, or whatever else is required for your simulation. Now, how do you simulate the beam-matter interaction? Well, as I mentioned before, if the particle is moving in vacuum or even through the magnetic fields, you can calculate it with a linear algebra. So if the particle is in vacuum, you just advance it to the edge of the material. Okay. Then, once the particle is at the edge of the material, you calculate the interaction cross-section of this particle with this specific material. And then you evaluate the so-called mean free path. So this is the typical path which the particle takes without interacting with material. Okay, so it depends obviously on the cross-section. The higher the cross-section, the lower the mean free path. Then you decide what steps do you want to take. So this can be just a mean free path itself, but it can be also a smaller step. And then typically during the particle propagates through the material, you have different types of interaction, right? So you have electromagnetic, you have strong interactions, and so you can decide what interaction you want to simulate in this specific step, and this is done usually also by a random number generator dependent on the cross section of every specific interaction. Then, once you simulate this interaction, you calculate what is the energy loss of the particle, and then you update, of course, the particle energy because it lost some energy, and direction. So you scatter the particles while they are interacting with the matter. Then you, if you generated any secondary particles, simulate them and add them to the stack of all the particles which you are simulating. And then you score the contribution in the observable which you want to see. So for example, if you have a detector and the particle already propagated to it, or if you want to see what is exactly the energy loss across the material, so then you can score the energy. And then you basically go back to the step 2, because the particle can continue propagating through the material unless the particle energy dropped below the threshold, which you have defined, or particle exits the geometry where the system is defined in general, right? At the end of the simulation, you want, of course, to get rid of all the particles. Now, a couple of slides on uncertainties. Here is an example of the proton beam hitting water, and you see that there are very different particles being generated. So you have strong interaction, electromagnetic interaction. And so if you simulate only one particle, then of course it will not be representative of a whole proton beam. So what you do is you simulate a number of particles. And here you see the energy, the dose deposited in the tissue as a function of depth. For the different numbers of initial protons, and you see that the error bars on the values decrease if you go to a higher number of primary particles. So the rule is, and this can be calculated statistically, that the error bars decrease with 1 over square root of number of particles you simulate. If you want to decrease the error bars by factor 2, like it is done between this diagram and this one, and then to the next one, then you have to increase the number of primaries by a factor 4. Okay, so this gets more and more computational heavy. In addition to statistical uncertainties, you also have systematic uncertainties. And these are dangerous because statistical uncertainties give you random errors, and they abide to the central limit theorem. And so if you increase the number of particles which you are simulating, then you can get rid of the statistical uncertainties to some degree, right? So if you think your error bars are too large, you can basically get rid of them by letting the computer run a little bit longer. However, if you have a systematic error, it can introduce some biases in your simulation, and that means that the value for which you are converging is wrong. And this you cannot get away with more computational power. Okay, they can result from many things. So this can be, for example, things which are part of your code or of your model, like what physics models did you adopt, what transport algorithms do you use, and also there are many unknowns in the cross section. So, for example, the cross section of beam with a specific material. If it's a very common material, will be measured quite precisely. But if it's a very uncommon material, and we were working, for example, at Power Institute on boron carbide as a degrader, there, of course, you basically have no data, right? So the uncertainties are huge. And a small error in uncertainties, like 10%, can result in a very large error in shielding efficiency. So, for example, if you have a shielding wall of 10 attenuation length, which is not very large, just 10% of the cross-section uncertainty results in a threefold difference in effectiveness. So this, because it's basically an exponential function. But there are also some user-made uncertainties. So you have incomplete knowledge of everything. For example, in hadron therapy, so I quote here Monty Python, the Life of Brian, where he says, "You are all individuals," and everybody says, "Yes." I inquire, "We're all individuals," and only one says, "Well, I'm not." So the thing is, of course, we approach medical physics as if every patient would be equal, but in reality, of course, the anatomy of every patient is slightly different. The tumor has different tissue, the density and the location of different organs and bones and muscle and fat tissue can be different. And so all these things have to be considered, and you cannot consider them all because you have, of course, a limited resolution when you are doing the MRI or CT scan. You have also changes in the patient. So the patient is breathing, the patient is moving. You do hyperfractionation, so you do many treatments, and then between one treatment and another, the patient is changing because of, for example, chemotherapy. They can lose weight, gain weight. If you are treating brain tumors, but they have a nose running because of a cold, then of course this is additional tissue in the way as well. So there is a bunch of things which you cannot predict very precisely. So you have to try to see what are the main parameters influencing your simulation and treatment plan, and then consider them. But you cannot, of course, invest an infinite effort to figure out any small deviation. So this is something which is difficult to learn directly, but comes with it with experience, that you learn which parameters are more important than the others. Okay, and we're progressing well. So now I can switch to the software codes which are used for Monte Carlo simulations. So there are basically 4 types of codes, and I show here, by the way, for every type only a limited number of examples. So this is by far not an exhaustive list. So you have mathematical codes where no beam physics is integrated. And if you want beam physics to be integrated, you have to do it yourself. So this includes MATLAB, Mathematica, or Python, very popular these days. There is a NumPy library, which is very powerful. Then you have codes which can simulate the propagation of the beam in order to design a beamline and also to match specific beam parameters. This includes transport, MEDEX, Agile and Twin Agile, or COSY. And then, based on these codes, often, but not always, you have tracking codes, which can track the distributions of the particles in specific beamlines, in specific fields, but they do not simulate the interaction of the beam with the matter. They usually simulate the absorption of particles when they reach, for example, the aperture of a magnet or of a kind of collimator, but they assume then that the particle is lost. And then you have the heavy-duty codes, which also simulate the beam-matter interaction. So this includes, for example, FLUCA or MCNP, or Gen4 and Gen4-based codes. And I will show a couple of examples in the coming slides. Now let's start with transport. Transport was developed in SLAC in the 70s. So SLAC is a Stanford laboratory for accelerated physics. And this is a code for beam optics calculation, and it's based on matrix multiplication. The input looks like that. So you have basically cards, and you calculate with these cards, or you give the parameters of the beamline and of the beam with these cards. The code can perform matching, and based on this code and based on this input, you also have a code which is called Turtle, which can simulate the propagation of the particles and the distributions of them, starting with, for example, some random distribution in the beginning, and then you can see what the distribution will be at any location.
Alex, 5 minutes?
Good. Yes, I will finish in 5 minutes.
Thank you.
Thank you. Then you have MEDEX. This is very popular code at CERN. It has an input which has a style of C++, and you can do some calculations. You can also perform matching, which is very important. And it has several tracking modules like track or PTC. And it can also produce output for survey, so that you know where to place the magnet, or you can tell it to your colleagues who are dealing with metrology. Then for the simulation of beam-matter interaction, I mentioned FLUCA before. So this is a Fortran-based tool, and it has large support community at CERN. There is also FLUCA School, so you can just use this link. It's very well calibrated. It's used by radiation protection worldwide, and also there is a player, basically user interface, which is very convenient. And this can be used for hadron therapy, but it's not very frequent that it's used for treatment planning systems. Jan4 is a code which initially comes from a detector development community, but has a functionality which is similar to FLUCA. So this is open source. This is developed in C++. This code is mostly used for some simulations of fundamental interaction with matter, but there are several codes which are based on Jan4, like for example, G4 beamline and BTSIM, which are mostly used for design of the beamlines, for design of the shielding, or TOPAS, which is used for nozzle design, monitors in front of the patient, and also beam interaction inside of the patient. So these codes can give you much more information than linear accelerator codes like MEDEX, but of course they cannot do a matching. So if you want to have specific beam parameters and want to vary, for example, magnetic fields in order to get these parameters, this code cannot deliver so simply the ideal solution for it, while MEDEX can. How do you select the code? Well, obviously, you check that the code has a correct functionality, so that it covers what it needs to do for your specific case. You also should check, ideally, if there is know-how at your lab or generally for this code, and if there is a support, because you will encounter some questions, some issues. You might want to visit a school, and so this depends on the support team if you will get this assistance or not. And another similar point is if there is a large user community, because if yes, there will be schools, there will be a lot of know-how, and also the code will be well calibrated, because if many people use it, the bugs are found more easily. And finally, what are interfaces to other groups or software packages which you need? For example, if your RP wants to use FLUCA, but your colleagues from the experiment want to use Jan4, then you might want to actually simulate the system in both of these codes. And this brings me to the benchmarking. So this is one of the reasons why you would want to have the same beamline in different codes, but also it helps you to avoid errors in implementation, right? So that you know that you have implemented the beamline correctly. And also you see that the code physics is correct or consistent. So you can cross-calibrate the physics models of different codes, and you are not very dependent on what specific cross-section is implemented in the code that you are using. Just a warning, beware of conventions. So if you are switching between the codes, we found that, for example, at PSI, that COSY, Transport, MEDEX, WinAgile, they have different definitions of the signs for quadrupole and sextupole field. So plus and minus are switched. Also, you have the Taylor expansion component, like 1/2 for sextuple, which you have to artificially introduce if you are switching from one code to another in some cases. So please check exactly how the fields are defined. And also the geometry can be defined differently. So for example, the beam path length is defined in MEDEX in dipoles along the circular curvature, while in Beach, which was previously used for alignment at CERN, it is defined as a straight line between entry and exit point. So you have a shorter distance then, and the position along that at the exit of the magnet will differ between these two codes. And again, check if the angles, for example, have a rotation of pi/2 or a different angle. So that brings me to my summary. Statistical processes determine a big share of what we deal in accelerator physics and in hadron therapy specifically. Monte Carlos are very powerful methods of simulating the statistical processes and of beam propagation outside of matter, in matter, and also in the detectors. And there is a wide variety of codes to pick from, so make a wise choice dependent on the specific problem which you are encountering. And this brings me to the end. So thank you very much for your attention, and I'm open to the questions.
So thank you so much, Alex, fulfilling our wishes and giving us a 101 on simulations. Just to say, I'm going to pass the discussion over to the students who are volunteering. But because we have a mixed audience in our participants who are in the course, this is why we asked you to walk us through all the steps. That we have a longer coffee break, so it gives them a chance to be able to ask you questions. And for students, please feel free to ask any question you want, be it simple or be it complicated. Alex will, of course, be able to answer because we know he can. And so from me, I pass it over to the students, and we will start at 11:30 with the next lecture by Professor Seiko. So Christophs, Cameron, Joe,
okay, thanks,
it's yours. Over to you.
Okay, thank you, Alex. That was a really interesting talk. Obviously, if anyone's got any questions, just stick your hand up and then you'll be able to ask Alex. And yep, okay, so we've got one in the chat from Code. I can just read it out. So it says, thank you for the great lecture. Please, how much maths must one know in order to be able to understand or use the Monte Carlo simulation tools for particle transport in medical physics?
Yeah, it's a very good question. This, I think, is an advantage of Monte Carlo compared with other approaches. So I covered before the reasons why people are using Monte Carlo. And the reason is basically if you can describe your beam and if you can describe the processes which are happening to your beam, then you do not need to calculate it yourself. The code basically will do it for you, and the higher the number of particles which you simulate, the lower will be the statistical errors. And this is, I think, the reason why Monte Carlo approach has been so successful in the recent years, because in order to do an analytical or spectral or numerical calculation, you have to be quite good in maths. You know, you have to know the numerical method or analytical integration method. So this is rather complex, and Monte Carlo allows you to basically put the distributions which you have, the materials which you have, the fundamental interactions, which are usually programmed in the code itself, and then let the computer do the calculation for you. So in that sense, it's a convenient tool.
Okay, thanks very much, Ad.
I hope it answers your question.
I'm sure it probably did. Okay, so next we got a question from Adam.
Hi, thanks for a really interesting summary of a huge area of topics. You mentioned for Monte Carlo codes, you're going to need to have like cross-section data. Who generates the cross-section data and how do they go about doing it? And also, how do you know it's correct?
Yes, also a very good question. The cross-section data is purely experimental. So you have usually some working groups within the community which is taking care of the code, which deals with it. So for example, I know it well for Fluka that there is a Fluka work package, which is specifically dedicated to calculation of, so basically benchmarking and input from experimental data. So sometimes it means that, for example, a new experiment is done, and one of the first things the experiment does is calculating the cross-section for this specific process, and then this is sort of advertised and people implement these results into the code. Sometimes the initiative is actually from the colleagues who are dealing with the code. So for example, the colleagues from Fluka, they have occasionally beam time in the north area, and they say, okay, we want to see how the neutrons of this specific energy are shielded by this specific density of iron, because it's done in many locations in the world, and we want to calibrate it a little bit more precisely. And so they do a dedicated experiment. So there is a STI group at CERN which is dealing with it. So sometimes it's the initiative of experiments, which is then being fed into the code, and sometimes it's the initiative of a code developers who say, we do a dedicated experiment to improve the knowledge of the cross sections. Yes, but the more frequent the process, the better it will be calibrated. So if you are dealing with lower energies and with very common materials like concrete, iron, water, then you can rely on these codes very well. If you are talking about energies of, let's say, PeV, and how they interact with some very exotic material, there will be basically no data. So it will be just a guess.
Okay, we have our next question from Florian.
Yes, thank you very much for this very nice lecture. I would have a question about these statistical uncertainties that you mentioned, that we can reduce by just simulating more particles. The question is, as you already mentioned, more particles means also a longer computation time. So it has to be some kind of a trade-off. And my question would be, is there a rule of thumb, or from your experience, where should you put this trade-off between having acceptably long computation times, but still having enough particles to have an acceptable statistical error? Where can we put this trade-off here?
Yes, a good question. Yes, it's more a question of the specific problem you want to address. So, for example, if your systematic uncertainties are in the order of 50%, you do not need statistical uncertainties below 1%, right? So if they are then in the order of 10%, then you are happy. And this is frequently the case with B-matter interaction. So I mentioned before, you have, for example, shielding efficiency easily a factor 3 of uncertainty even in well-calibrated systems. So that is one of the parameters which influences the decision. The other one is how much calculation power do you have and do you need? So usually the most reasonable approach is you do a calculation with a low number of particles in the beginning, just to see if your system performs as expected, if your assumptions are rather correct, and if the distributions you get roughly make sense. So once you know that the simulation you do is correct, and then you want to basically have more precise results for a paper, for a presentation, then you redo the final simulation, which you know is correct, but with much higher number of particles. And this often means you just set it up Friday evening, and the computer calculates the whole weekend, and you come Monday morning and see the result. But of course, it would be nonsense if you are just trying out the simulation and building it up to let it each time run 2.5 days. So you want to in the beginning, when you are setting it up, probably have large statistical uncertainties for the sake of better computational time. And then once you are certain that what you are calculating makes sense, then you can reduce them by letting the final simulation run longer.
All right, thank you.
You're welcome.
Okay, our next question is from Kristaps.
Thank you for the very nice presentation. I guess my question is sort of a bit of a continuation of what Adam already asked. It's also related to cross sections. It's more practical, I would say. Like, from your experience, is there like some clear areas where we really are missing like cross-sectional data? Because I mean, through going through literature, since I'm a bit focused on helium ions, there's like, for example, like helium ion interaction with matter, like the cross-sectional data there are not as well defined as it was for protons or carbon ions. And so the question is, like, from your experience, where are we mainly lacking the cross-sectional data if we're talking about the medical physics field?
Mm-hmm. Yes, a good question indeed. And I think the answer can be summarized with what I've mentioned before. Where you have a lot of experience and a lot of experiments, there you would usually have better data. So in the medical community, there is a big discussion about the LET, so linear energy transfer, and RBE, the relative biological effectiveness of different particle types, for example. And there, the knowledge is much more precise for X-rays, and it's reasonably good for protons. But if you go to exotic ions, then the amount of knowledge is very little. So try to find a radiobiological effectiveness of lead ions, for example. You will not easily find this data, because also the mechanism of actions are not even so well understood. So basically, if you are doing on a fundamental scale something which has been done by many groups, like, for example, interaction of protons with water, then you can rely on the cross-sections being very well calibrated. While if you are going into a new domain, so helium is a good example, because helium was around for a long time, but there is much less data on patient treatments with helium than with protons or even with carbon and oxygen, right? So there might be indeed areas where the data is missing. And so if you notice these areas and you have a possibility to do an experiment or collaborate with somebody who can do the experiment, then it might be a very reasonable input. So then you can do a research project on determining cross-section or LAT of helium beams.
Okay, thank you.
You're welcome.
Okay. Our next question is from Celine.
Hi, thank you very much for this interesting talk. I have a short statistical question. I know I'm scratching the surface of a very large topic. You mentioned the bias variance trade-off directly in the beginning, and there are a lot of goodness of fits stuff around. And for me, it's always hard to find the right one for like my data I have. I'm mostly working with very low statistics, so I don't have that much data points. And so my question is there like a guideline or something which can help me through this process to find the right goodness of fit test?
Yeah, well, I cannot recommend some specific paper or some specific guideline, but the rule of thumb is do not overmatch. So try to use the simplest system or the simplest approximation which delivers comparable test results, right? So you train your algorithm with something and you test it, and then try to stay as low in complexity as possible. Do not overcomplexify unless you have reasons to assume that there are complex physical processes behind it, right? So here I spoke about polynomials and exponent of the polynomial, but of course the fitting function can be anything. It can be exponential, it can be a Gaussian, and especially in physics. So this example, price versus square footage, there is no governing laws why price has to be, let's say, a quadratic function or exponential function of square footage. But in physics, you usually have some physical underlying processes, and these underlying processes have some systematics. So just from the fundamental physics point of view, the potential of an electron in a shell is 1 over r, right? So this influences how the beam interacts with the electrons in matter. And so sometimes if you have a suspicion that such processes have direct influence on the process you're trying to simulate, then you can use these functions like 1 over r for the matching. But again, just try to be as simple as possible, and especially if you have very little data, do not overmatch, because you will the predictive power of the model you develop will be low.
Okay, thank you very much.
You're very welcome.
Okay, we just got one more question in the chat from Valeria, who said, I've heard about the recent use of artificial intelligence for Monte Carlo simulations. How can this help us, and what's the status of artificial intelligence in this context?
Yeah, it's a very general question. So these two slides are actually from Dr. Ratner from Fleck, and the talk he gave was actually on the topic of artificial intelligence. So indeed, many of the problems which we encounter in generating Monte Carlo data or trying to simulate things result or pin down to the same questions which you are dealing with when you're trying to program artificial intelligence algorithms, namely what models are appropriate to simulate processes or to predict certain outcomes. So on this fundamental level, you have a big overlap. Now, if you are trying to, for example, find a specific solution with help of AI and with help of Monte Carlo, this is more of a practical question of computational power, because Monte Carlo needs a lot of computation, and then AI usually also approaches things from the trial and error approach, right? So it doesn't have some systematic models which it assumes, but it rather looks at all the data and then is trying to generalize it. And so because of that, you need to run a large number of Monte Carlo simulation in order to have a reasonable model. So this makes it very calculationally intense. So it might get better again if the calculational power increases as it did in the last decades. But another concern which many people have with AI is if it develops models, it's a little bit of a black box. You have input parameters, you have output parameters, but you do not understand exactly what is happening in between. And so this is fine if it works, if you do a prediction and it turns out to be correct. But if it doesn't work, it's very difficult to find where is exactly the problem. Is it the cross-section? Is it my implementation? Is it a bug? Is it a convention? Even something like a sign. So and combining their Monte Carlo with artificial intelligence can make it a little bit intransparent as well, because the Monte Carlo, with all its advantages in let's say easiness of use, it still gives you a little bit less of understanding of how the underlying processes work if you compare it with other methods like analytical solutions, numerical integration, etc. Because you basically you do not try to solve the equations by yourself, but you just program them into the code. And if you combine it also with artificial intelligence, which also has this sort of black box approach, it can make the what your computer does a little bit intransparent. So, but this is a vague statement. So I hope it answers your question. But yeah, it's more of a feeling which I have from talking people in the with the people in the field than a specific approach which one should recommend or not.
Okay, yep, thanks. Yep, that's, I just had that questions be answered. I think that's everything in terms of the formal questions. Can't see anything else on Slack either. So, I mean, as manager was saying, we've got an extended coffee break, so obviously very welcome to continue to ask Alex anything if you'd like. I've actually got, it's actually just related to the previous point. So in terms of practically implementing this artificial intelligence, is it actually done sort of via GANT and C itself, or would you sort of have to export things to another code to carry out this machine learning, or how would it actually practically be done, or does it really just depend on the context?
Well, I do not know of the Monte Carlo codes for beam physics which already have artificial intelligence modules. So if you look at this list of codes from these three categories, I do not know of any code which has artificial intelligence. I know Opal has some genetic algorithms which are strictly speaking not part of artificial intelligence. However, of course, if you look at the general mathematical codes which you can use for simulation of the beam propagation, simulation of beam-matter interaction, then some of them, especially Python, is extremely heavily used for artificial intelligence. I think a big share of programming for artificial intelligence nowadays is done in Python. So there, of course, if you want to do something, let's say, rather on the fundamental side of physics, there you can use artificial intelligence as well. And I say fundamental part of physics because, of course, if you start with Python, it's such a general code that all the cross sections, all the physical processes which you have in Fluka and Jan4, which took decades to implement, well, you would need to implement yourself if you need them, right? So what you probably end up with is a very limited number of physics processes which you simulate, but then with a, of course, add-on that you can apply artificial intelligence on it.
Okay, thanks a lot.
Yeah, I was going to say, if there are no questions for students, may I ask a question?
Yeah, of course. I don't want to say more student questions.
No, I just want to make sure that I don't take the student time.
It's all good.
Okay, so if so good. So Alex, thanks again. So I have a question, not directly related to what you're discussing, but the idea of the fact that these simulations could be applied to almost any field, anything. So as you know, I'm working on a project for developing countries. The machines break down a lot, you know, collimators to electric guns, power shortages, and all sorts of things. Can one get sufficient data and simulate and analyze it in such a way that one could predict before the breakdowns occur? And if so, how would one go about doing that?
Yes. So this is a question which is clearly, again, not in the domain of these three categories of the code. So it's less about the simulation of beam propagation or beam-matter interaction, but much more a fundamental, let's say, requiring some fundamental mathematical calculation. So rather in the category of the third code. And there, of course, your input data is not a distribution of the beam or the cross-section of the beam with some specific matter, but it's rather, okay, what are the observable parameters which I have, like, for example, temperature of the different components, or the breakdown rate of the different components, or whatever you can, the movement of a multi-leaf collimator. So all these parameters are serving as a input. And then, of course, as an output, you want to have a prediction of what will break down next. And this is done at several labs. I know at CERN there is an initiative for that. At PSI, there was a study on that. At SLAC, they have actually successfully predicted several distributions of, let's say, of beams, but also several systems which can break down. And so then, if you know that, for example, in the chances of the system to break down during the next month is high enough, 20%, then during the next maintenance, you just exchange the system in order to avoid this breakdown. So from what I heard from the colleagues, it has currently still a very limited number of applications, just because the parameters which you can monitor are very limited. But for these applications, it sometimes delivers results which a human intelligence would not. So if you let an expert even look at, let's say, what is the distribution of these parameters, like, for example, how often did we move the multi-leaf collimator last week, and then from this curve to estimate when will it get stuck next time, a human can predict it less good than an eye.
This is the sort of thing I was thinking of, using either also combination machine learning, AI, and so on, because a lot of these countries don't have the spare parts. But if they knew 2 or 3 months ahead of time, because it can take quite a long time to get the spare parts, whether this could be a way of, early alert system, so to speak. Thanks,
yes.
Alex.
Yes, so we're currently, for example, addressing it with one of the commercial vendors for particle therapy, how they can predict the breakdown of the components in the series of machines which they have worldwide. And of course, the bigger the pool, the more precise data you get, right? So it's always good if you base your data sets on very large amounts of data. And also for the third world countries, I think it's an excellent initiative, because you cannot simply transport the components within one day, but of course you can simply transport the code. So if they have the same systems and the same observables, and you have already a code, for example, for Electa machine, which knows roughly when the breakdown will happen, this would help them tremendously, because then the supply lines can be addressed in advance.
Thank you for that. Looking for collaborations for that. Anyway, sorry.
Certainly, with great pleasure.
Okay.
So, Manjit, maybe I make a comment to your request. I don't know if you know about FEMA, F-M-E-A, the failure mode event analysis that was developed in the 1940s during World War II by the Americans, that became very heavily used by NASA for predicting failure of the space shuttle. So this has become heavily used in many hospitals in the US, where they try to predict when there's going to be failure of equipment, and it's not a straightforward problem. So I think you have a big problem in your hand.
Otherwise, it would already be solved.
Exactly. So I would suggest you look up FEMA. It's really very important. I'll write it in the chat.
Thanks, Joao. Can you maybe offline? You will also send me some reference to a paper as well. That would be really great. Thanks.
It's very common for NASA to do that, and all these big companies now for engineering, because they want to predict when problems happen. It's not so easy, and it's become common in hospitals too, also in the US.
Yeah. Thanks a lot.
I'll send you some details.
Yes, please. Thanks a lot, Joe.
I see. Chris Tubbs has also got another question.
Yeah, thank you. I guess this could be a bit broader question. I'll try to ask the question correctly. Firstly, it's a bit, I guess, related to commissioning of new machines. So I mean, I had some experience in commissioning like photon machines, and it's like in the end when you use commercial algorithms, it's like sort of the idea is to match your measurements to your simulations. And of course we're not talking Monte Carlo or full transport simulations there, but it's sort of to match them, you sort of do not really physically based things, you just sort of adapt some parameters, not really thinking about the physics. So the question is, I mean, what would be your take on that? Like if we are commissioning a whole new treatment facility and we have our measurements and they don't quite fit with our model, would you recommend to do like in-depth analysis where it arises from the physics point of view, like we should change something in the beamline or our physics models, or it's okay to just do some tweaks just to match the data?
Yeah, very good question. There is always a mismatch between simulation and reality. Simulation is a model-based approximation of what you can expect in the reality, but it's only as good as your as the input which you deliver. Now, in reality, of course, you have all possible errors. You have misalignments, you have beam source creation errors, you have beam deviations. The quadruples have maybe a wrong gradient, etc. But then you also have a very strong problems, like for example, the polarity of a quadrupole is wrong, or one pole doesn't have a connection. You know, these things are huge. They impact your beam significantly. So I think the correct approach is you always have a model and a simulation, and then you start with this model, and then you see that the beam is slightly not as it should be, in ideal case, and then you tweak the parameters. So this tweaking can compensate for the imperfections you have. For example, if you have to be two I curves, so the magnetic field, how it depends on the current of the quadrupoles or dipoles, and if this is not precise, you need to do the tweaking, but you do not know if it will be precise or not in advance. Your colleagues who are measuring the magnet do their best work, but of course, the Hall probes have limited resolution. Their ampermeters have very limited resolution. There is a hysteresis curve, so there are there is a large number of small higher order effects which impact it. And so to compensate for it, you can do the tweaking, and then you can just say, well, okay, I do maybe even a random or AI-based approach to this tweaking, and the final result is what I want to have, and then it delivers me the result. However, if this tweaking becomes excessive, if you see that, for example, the field you need is suddenly double of what you would expect, or the collimator size is different, or the beam intensity is only one factor of 1/10 of what it's supposed to be, then it means that something is seriously off with the model, and there it can be concerning. So there it's worth finding out what the reason is. I'll just give you an example. So we had a problem at CERN with transmission of the beam, and we saw that we basically get what we need, but the beam is not flat or not Gaussian until so the intensity is factor 10 below what we wanted it to have. So we started working on it because we were not happy with the precision of the model, especially if you have intensity difference of factor 10. And what we figured out is that one of the collimators where we didn't have diagnostics, the beam was strongly off for some reason, so probably one of these B2I curves. And that meant that from a Gaussian, you were cutting only a small part. And so if we would have left the settings as they are, and then for some reasons the Gaussian would move into the collimator, you would have a sudden increase of intensity by factor 10, which would have killed the detector, which was outside. And the same, of course, if you do it for the patient, even more important, you want to control the parameters well. So you don't want a sudden change of factor 10 in intensity. So if the parameters, the differences between the parameters on the scale, which is not justifiable by some sort of minor offsets, then you might want to investigate what the actual causes for it are. But if it's just, again, the tweaking by a couple of per mil here and there, and the beam size is off by a couple of percent, this usually is just a question of experimentation and good commissioning, that you indeed do all the scans and figure out what are experimental parameters which correspond to the model. Does it answer your question?
Yeah. Thank you.
Okay.
Thank you very
Super.
much.
Okay, thanks a lot, Alex. I think that's actually all our questions addressed. So thanks so much, especially for spending the extra 20 minutes as well.
Joe has lifted his hand, but then has
He's
removed
changed
it.
his mind.
Okay. Well, Joe, if you want to, please speak up.
I think we're good. Yeah. Of course, if anyone's got any additional questions, we can always put them in Slack as well once we've had time for the lecture to settle. Aside from that, again, thanks for your time, Alex. I think we'll reconvene in about, well, 10 minutes for our next lecture, which starts at 11:30.
Very good. And if you have more questions or any comments, then please just use this email address. An email.
And the Slack chat. Thanks a lot, Alex. Really appreciate this.
Thanks a lot.
Thanks very much.
Thank you very much.
Goodbye. Thank you.
So we'll